When determining the appropriate number of parallel conductors for a 4000 amp service, different interpretations of the National Electrical Code, or NEC, can lead to varying conclusions. An engineer suggested using 15 parallel 500 kcml copper conductors, citing Table B310.7 from Annex B as justification. The local utility company, on the other hand, proposed using 11 parallel 500 kcml copper conductors, referencing Table 310.16. Understanding the nuances of these tables and their applicability is crucial for making the correct decision. NEC Section 310.15a allows ampacities for conductors to be determined either by tables or under engineering supervision, as detailed in 310.15b and c. This flexibility means that both approaches have potential validity provided they are applied correctly. The core of the debate lies in which table is most appropriate for the given scenario, which involves an underground service. Table 310.16 outlines ampacities for conductors in raceways or cables based on their size and insulation type. For a 500 kcml copper conductor, this table provides a specific ampacity value. In contrast, Table B310.7 details ampacities for conductors in free air, considering factors like conductor type, size, and grouping. For the engineer's position, Table B310.7 from Annex B is used to provide ampacities based on conductor type, size, and grouping. It argues that for 500 kcml copper conductors in a parallel configuration, Table B310.7 requires 15 conductors to carry 4000 amps. For the utility company's position, Table 310.16 is used, which provides ampacities for raceways and cables based on their size and insulation type. It argues that Table 310.16 allows for 11 parallel 500 kcml copper conductors to carry 4000 amps. To determine the correct approach, one must consider the installation type. Since the service is underground, the conductors are most likely installed in a raceway or cable tray. Given this installation method, Table 310.16 becomes the more relevant reference. Let's delve deeper into each of these tables. Table 310.16, as mentioned, is specifically designed for conductors installed in raceways or cables. This table considers the heat dissipation characteristics of conductors enclosed within a raceway, which directly impacts their ampacity. The table lists ampacities for various conductor sizes and insulation types, taking into account the number of conductors in the raceway. In contrast, Table B310.7 focuses on conductors in free air. This scenario assumes that the conductors have ample space to dissipate heat, resulting in higher ampacity ratings compared to conductors in raceways. Using this table for an underground service, where conductors are typically enclosed, would not accurately reflect the actual thermal conditions. Let's analyze the ampacity of a 500 kcml copper conductor based on Table 310.16. Depending on the specific insulation type and temperature rating, the ampacity for a 500 kcml copper conductor in a raceway is approximately 380 amps to 430 amps. For the sake of demonstration, we'll use 400 amps. If each 500 kcml conductor can carry 400 amps, then 10 parallel conductors would be sufficient to carry the 4000 amp load, because 400 amps multiplied by 10 conductors equals 4000 amps. It's important to consult the specific table based on the conductor's insulation type and temperature rating to get the precise ampacity value. Now let's consider the conditions under which Table B310.7 would be applicable. This table is primarily used for open-air installations where conductors are exposed to free air circulation. Examples include overhead transmission lines or conductors supported by insulators in a large, open space. In these scenarios, the heat generated by the conductors can readily dissipate into the surrounding air, allowing for higher ampacities. However, for an underground service, these conditions do not exist. The conductors are typically buried or installed in conduit, which restricts airflow and increases the ambient temperature around the conductors. Therefore, applying Table B310.7 in this situation would lead to an overestimation of the conductor's ampacity. To summarize, The choice between Table 310.16 and Table B 310.7 depends on the installation type. For underground services, where conductors are typically enclosed in raceways or cables, Table 310.16 is the more appropriate choice. This table accurately reflects the thermal conditions and provides ampacity ratings that are suitable for this type of installation. In contrast, Table B 310.7 is intended for open-air installations where conductors have ample space to dissipate heat. Applying this table to an underground service would result in an overestimation of the conductor's ampacity and could potentially lead to unsafe conditions. Remember that the NEC provides guidelines and standards for electrical installations, but it is ultimately the responsibility of qualified electrical professionals to interpret and apply these codes correctly. Consulting with experienced engineers and inspectors is crucial for ensuring that electrical installations are safe, reliable, and compliant with all applicable regulations. In conclusion, when sizing parallel conductors for an underground 4000 amp service, it is imperative to consider the installation type and select the appropriate ampacity table. Table 310.16, which is designed for conductors in raceways or cables, is the more relevant choice for underground services. This table provides ampacity ratings that accurately reflect the thermal conditions and ensure that the conductors are adequately sized to carry the intended load. It is also important to consider the specific insulation type and temperature rating of the conductors when determining their ampacity. Consulting with qualified electrical professionals is always recommended to ensure that electrical installations are safe, reliable, and compliant with all applicable codes and regulations. Firstly, you need to identify the installation type. This is a critical first step in determining which table is applicable. Is the installation an underground service, or is it something else? Secondly, select the appropriate ampacity table based on the installation type. Table 310.16 is designed for conductors in raceways or cables and is suitable for underground services. Table B 310.7 is intended for open-air installations. Thirdly, consider the insulation type and temperature rating of the conductors. These factors will affect the ampacity of the conductors, and you will need to consult the specific table for the correct ampacity values. Fourthly, calculate the number of parallel conductors required based on the ampacity of the conductors and the total load. Make sure that the conductors are sized adequately to carry the intended load. Fifthly, consult with qualified electrical professionals to ensure that the electrical installation is safe, reliable, and compliant with all applicable codes and regulations. This will help to ensure that the installation is done correctly and that any potential problems are identified and addressed. By following these steps, you can ensure that you select the correct ampacity table and size the parallel conductors appropriately for an underground 4000 amp service. This will help to ensure that the electrical installation is safe, reliable, and compliant with all applicable codes and regulations. Now let's discuss some additional factors that may influence the selection of parallel conductors. One important factor is voltage drop. Voltage drop occurs when the voltage at the load is less than the voltage at the source. This can be caused by the resistance of the conductors, and it can be exacerbated by long conductor runs or high loads. To minimize voltage drop, it is important to select conductors that are large enough to carry the load without excessive voltage drop. The NEC provides guidelines for voltage drop in branch circuits and feeders. Another factor to consider is the ambient temperature. The ambient temperature is the temperature of the air surrounding the conductors. Higher ambient temperatures can reduce the ampacity of conductors, as the conductors are less able to dissipate heat. The NEC provides correction factors for ampacity based on ambient temperature. These correction factors must be applied to the ampacity values in the tables to account for the effects of ambient temperature. Another important consideration is the type of load being served. Some loads, such as motors, can draw large inrush currents when they are started. These inrush currents can cause voltage dips and can potentially damage equipment. To mitigate these effects, it is important to select conductors that are large enough to handle the inrush currents. The NEC provides guidelines for sizing conductors for motor loads. Finally, it is important to consider the future needs of the electrical system. If it is anticipated that the load will increase in the future, it is important to select conductors that are large enough to handle the increased load. This will help to avoid the need to replace the conductors in the future. In addition to these factors, it is also important to consider the cost of the conductors. Larger conductors are more expensive than smaller conductors. Therefore, it is important to strike a balance between the cost of the conductors and the performance requirements of the electrical system. By carefully considering all of these factors, you can select the parallel conductors that are best suited for your specific application. This will help to ensure that the electrical system is safe, reliable, and efficient. Remember that the selection of parallel conductors is a complex process that requires careful consideration of a variety of factors. Consulting with qualified electrical professionals is always recommended to ensure that the electrical installation is safe, reliable, and compliant with all applicable codes and regulations. To further elaborate, let's examine the specific requirements outlined in NEC Article 310, which covers conductors for general wiring. This article provides detailed information on conductor ampacity, directing factors, and installation requirements. Understanding these requirements is essential for ensuring that parallel conductors are sized and installed correctly. One of the key concepts in Article 310 is the ampacity directing factor. Ampacity directing is the process of reducing the allowable ampacity of a conductor to account for factors such as ambient temperature, the number of conductors in a raceway, and the presence of other heat-generating equipment. The NEC provides specific directing factors for various conditions. These factors must be applied to the ampacity values in the tables to determine the allowable ampacity of the conductor under the specific conditions. For example, if a raceway contains more than 3 current-carrying conductors, the ampacity of each conductor must be derated. The derating factor depends on the number of conductors in the raceway. Similarly, if the ambient temperature is higher than the temperature rating of the conductor, the ampacity of the conductor must be derated. Another important aspect of Article 310 is the requirement for proper conductor identification. All conductors must be clearly identified as to their purpose, such as phase conductors, neutral conductors, or equipment grounding conductors. This identification is typically achieved through the use of colored insulation or markings. Proper conductor identification is essential for safety and for ensuring that the electrical system is properly maintained. In addition to these requirements, Article 310 also specifies the minimum size of conductors for various applications. The minimum size of conductors depends on the load being served and the length of the conductor run. The NEC provides tables and formulas for determining the minimum size of conductors. It is important to select conductors that are large enough to carry the load without exceeding their allowable ampacity or causing excessive voltage drop. Furthermore, Article 310 addresses the installation requirements for conductors. Conductors must be installed in a manner that protects them from physical damage and prevents them from coming into contact with flammable materials. Conductors must also be properly supported and secured to prevent them from sagging or coming loose. The installation requirements for conductors vary depending on the type of installation, such as underground, overhead, or in raceways. By adhering to the requirements outlined in NEC Article 310, electrical professionals can ensure that conductors are sized, installed, and protected in a manner that promotes safety and reliability. This article provides a comprehensive framework for conductor selection and installation, and it is essential reading for anyone involved in electrical work. To delve even further, let's consider the specific requirements for parallel conductors. When conductors are installed in parallel, certain additional requirements must be met to ensure that the current is evenly distributed among the conductors. The NEC specifies that all parallel conductors must be the same length, the same conductor size, the same insulation type, and the same termination method. These requirements are intended to minimize impedance imbalances among the parallel conductors. Impedance imbalances can cause unequal current sharing, which can lead to overheating and premature failure of the conductors. To minimize impedance imbalances, it is also important to ensure that the parallel conductors are installed in close proximity to each other. This can be achieved by bundling the conductors together or by installing them in the same raceway. The NEC also specifies the maximum number of conductors that can be installed in parallel. The maximum number of parallel conductors depends on the size of the conductors and the type of installation. For example, the NEC typically limits the number of parallel conductors to 3 or 4 per phase. When installing parallel conductors, it is important to use proper termination methods. The conductors must be terminated in a manner that provides a reliable electrical connection and minimizes the risk of overheating. The NEC provides specific requirements for terminating parallel conductors. These requirements vary depending on the type of termination being used. In addition to these requirements, it is also important to consider the coordination of overcurrent protection devices. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect conductors from overloads and short circuits. When conductors are installed in parallel, the overcurrent protection devices must be coordinated to ensure that they provide adequate protection for all of the conductors. The NEC provides guidelines for coordinating overcurrent protection devices in parallel conductor applications. By following these requirements and guidelines, electrical professionals can ensure that parallel conductors are installed in a safe and reliable manner. Parallel conductors can be a cost-effective solution for increasing the ampacity of an electrical system, but it is important to adhere to the NEC requirements to ensure that the system is properly designed and installed. Now let's discuss the role of engineering supervision in conductor sizing. While the NEC provides tables and guidelines for conductor sizing, it also allows for engineering supervision to be used in determining conductor ampacity. Engineering supervision can be used to deviate from the NEC tables and guidelines, provided that the engineering analysis demonstrates that the conductors are adequately sized for the specific application. Engineering supervision is typically used in complex electrical systems where the NEC tables and guidelines may not be directly applicable. For example, engineering supervision may be used to determine the ampacity of conductors in high-rise buildings, industrial facilities, or data centers. When engineering supervision is used, the engineer must document the analysis and calculations that support the conductor sizing. The documentation must be submitted to the authority having jurisdiction for review and approval. The authority having jurisdiction is the local government agency that enforces the NEC. Engineering supervision can provide flexibility in conductor sizing, but it is important to ensure that the engineering analysis is sound and that the conductors are adequately sized for the specific application. It is also important to consult with the authority having jurisdiction to ensure that the proposed conductor sizing is acceptable. In the context of the original question, the engineer's reliance on Table B310.7 from Annex B may be justified under engineering supervision if the engineer can demonstrate that the conductors will be adequately cooled in the specific installation. However, the engineer must provide documentation to support this claim. In the absence of such documentation, the utility company's position, which is based on Table 310.16, is likely the more conservative and appropriate approach. The decision of whether to use engineering supervision or to rely on the NEC tables and guidelines depends on the complexity of the electrical system and the level of expertise of the electrical professionals involved. In complex systems, engineering supervision may be necessary to ensure that the conductors are adequately sized. In simpler systems, the NEC tables and guidelines may be sufficient. Regardless of the approach used, it is important to prioritize safety and to ensure that the electrical system is designed and installed in accordance with all applicable codes and regulations. Furthermore, let's address the importance of coordination with the local utility company. When designing and installing electrical services, it is essential to coordinate with the local utility company. The utility company is responsible for providing electrical power to the building, and there are specific requirements for the electrical service entrance. The utility company may have specific requirements for the size and type of conductors used in the service entrance, as well as the location of the service disconnect. It is important to consult with the utility company early in the design process to ensure that the electrical service meets their requirements. In the context of the original question, the utility company's position on conductor sizing is likely based on their experience with similar installations in the area. The utility company may have data on the actual load demand of similar buildings, and they may have specific requirements for conductor sizing to ensure that the electrical service is reliable and can meet the peak load demand. Coordinating with the utility company can help to avoid delays and cost overruns during the construction process. It can also help to ensure that the electrical service is properly designed and installed. In some cases, the utility company may require the electrical contractor to submit plans and specifications for the electrical service for their review and approval. This review process can help to identify any potential problems or discrepancies before construction begins. In addition to coordinating with the utility company, it is also important to coordinate with other trades involved in the construction project. For example, the electrical contractor must coordinate with the mechanical contractor to ensure that the electrical service can support the HVAC equipment. The electrical contractor must also coordinate with the plumbing contractor to ensure that the electrical service can support the water heaters and pumps. Proper coordination among the trades can help to avoid conflicts and delays during the construction process. It can also help to ensure that the building systems are properly integrated and that they function efficiently. In conclusion, the design and installation of electrical services is a complex process that requires careful consideration of a variety of factors. It is important to consult with qualified electrical professionals, to coordinate with the local utility company, and to coordinate with other trades involved in the construction project. By following these steps, you can ensure that the electrical service is safe, reliable, and compliant with all applicable codes and regulations.